let me just remind you of where we were last time. We were looking at the spin in a magnetic field. And we just said that the magnetic field, suppose it's uniform, so B0 is some constant value, and the magnetic field is in the z direction. Okay, the Hamiltonian H is minus mu dot B. Okay, so that's going to give me just the z component of mu, so it's going to be minus mu sub z B0. Okay, so how is mu and the angular momentum related? Okay, so remember that we had this relation. Mu is equal to E over 2m times, well, actually we called it gamma, so let me just call it gamma so that we are consistent with what we are doing last time. So mu, remember, was equal to gamma times the s, okay, the spin vector, component by component. And the gamma was equal to E over 2m times this g factor. Okay, and the g factor for the electron was something extremely close to 2. Okay, it's 2.00 something. Okay, there's a minus sign involved because charge of the electron is negative, so the magnetic moment is in opposite direction to the spin. Okay, so putting all of those things in, I just look at the z component of this, so h becomes equal to minus gamma sz times b0. Or I can write this as minus gamma h bar over 2 times sigma z, where sigma is the Pauli matrix, times b0. Okay? So, looking at this, if I want to find the eigenfunctions of this, it's very easy. It's the eigenfunctions of sigma z. So there are two eigenvalues, one for sigma z equal to +1, another for sigma z equal to -1. So I'm going to get two energy levels. Okay, so the energy levels are going to be for the eigenvalue equal to +1, I'm going to get minus gamma h bar over 2 b0, and for sigma z equal to -1, I'm going to get gamma h bar over 2 b0. Just remember that this GE has in it a minus sign, so the gamma itself is negative, so the minus gamma state is higher energy than the other one. Okay, so this corresponds to the up z, okay, state, or just up, okay, or if you don't write anything, the default is the z direction, and this is the down z, and remember this is associated with a vector 1, 0, and that's associated with 0, 1. Okay, so that's basically the where we were last time. Okay, we generated all of this. Okay, so what I want to do now is I want to solve a time-dependent problem. Okay, so let me pose the problem here. So suppose at time equal to 0, my spin state is in the up x state. Okay? So up x state, remember, is just 1 over square root of 2 up z plus down z like this. Okay, so I already know its expansion in terms of the eigenstates of the Hamiltonian. Okay, so these are the eigenstates of the Hamiltonian. It's a sigma x. So at time equal to 0, suppose I made a measurement and I found out that the x measurement gave me plus h bar over 2. So I know that the spin is in the plus x state. Okay, so the question is, what is the time dependence of this? Well, since I know the expansion of this thing in terms of the eigenstates, I can easily write down the time dependence, right? It's going to be 1 over root 2. Okay, so I have to multiply this by the corresponding factor, e to the minus, so it makes the plus I gamma h bar over 2 b0, so that's the energy, times t divided by h bar. So these h bars cancel. Okay, up. And then I have plus e to the minus same thing, minus I gamma b0 over 2 t down. Okay, so this is how the state develops in time. Now, what can I do with the state? Okay, obviously it's changing, and I know how to write down various components of the spin eigenvectors in terms of the spin z eigenvectors. But let's just look at some things that, okay, let me just keep that over here. Okay, so let's look at something like what am I going to get, for example, for the expectation value of x. Okay, expectation value of the spin operator in the x direction. Now, again, let's just remember physically what's going on here. We have the magnetic field, which is in the z direction. And I just measured the x component of the spin, and I found out that the spin was plus h bar over 2 in the x direction. And now I'm interested in looking at what the expectation value of that is as a function of time. So at time equal to 0, I already know that this spin has a value plus h bar over 2, and it's measured in the x direction. So I should start, okay, this should start from h bar over 2, okay, at time equal to 0. Let's see what happens as a function of time. Okay, so how do I calculate this? Well, I just have to put in this chi of t, right, as x chi of t, and find out what that expectation value is. All right, so let's just put those things down. There's a 1 over square root of 2 from each one of the ket and the bra. So let me write that as 1 over 2. Okay, then I have this whole thing. Let me write that out. E to the I gamma b0 over 2 t, right? That's it. And complex conjugate, so I have to put a minus sign. And then I have up bra. Then I have plus e to the I gamma b0 over 2 t down bra. Then Sx, then this thing again, e to the plus I gamma b0 t over 2 and upspin plus e to the minus I gamma b0 t over 2 and a downspin. Okay, I have the complex conjugate values over there and the adjoints for the vectors. So that's what I have. So now I have to find the expectation value of this Sx in between the states, the eigenstates of the Sz operator. But we know what Sx looks like in that representation, right? Sx, remember, looks like h bar over 2, 0, 1, 1, 0. Okay, so what does that mean? Remember, these are just the expectation values, well, not the expectation, the matrix elements of Sx. So this, remember, has an upspin on the right, downspin on the left, upspin, downspin. So the diagonal terms are always 0, okay, and the finite terms are up, down, and down, up, which both give 1, right? Okay, so that means the only finite terms that I'm going to get are going to be up and down, over there, and down and up. Okay, and they will give me 1. So what do I get? I get 1 over 2. All right, the inner product of this with that gives me e to the minus I gamma b0 t. Okay, and then the other one gives me e to the plus, excuse me, e to the plus I gamma b0 t. Okay, so indeed I get a cosine function. So I get cosine, let's call it omega L t, where omega L is this quantity gamma times b0, which is called the Larmor frequency. Okay, so what's happening? The object, okay, has a time equal to 0, as you would expect. I forgot the h bar over 2's, right, from the matrix elements. Okay, so I'm going to get h bar over 2. So this expectation value is going to be h bar over 2 at time equal to 0, but then it will decrease, and in fact it will become minus h bar over 2, which means that at a later time I'm going to have the spin pointing in the minus x direction. Okay, so, but what happens in between? Okay, so suppose I want to also find out the expectation value of Sy, right? Let's make an attempt at that. Okay, so what is the expectation value of Sy? Okay, it's going to be basically the same thing. There's a 1 over 2 out in front, and then I'll just copy the same stuff, e to the minus I gamma b0 over 2t, up, bra, up, and then I have plus e to the I gamma b0 over 2t. Okay, these are the complex conjugate terms. Comes in with a downspin. And then I have this Sy now for the expectation value, and the same thing now in the ordinary space, not the adjoint space, but b0 over 2t up ket plus e to the minus I gamma b0 over 2t down ket. So we go through the same arguments. Yes?
Didn't we write chi of t in the x representation up and down?
No, these are the z representations. Remember? Okay, we solve this. Okay, so the problem we are solving is this problem. Okay, so we are putting the chi at, okay, time equal to 0 equal to up x, which is written like this. Okay, so we are still doing the same problem, okay, same time development of the ket, but now we are looking at the expectation value of a different operator. Okay, so the argument is the same. We had this Sx, the matrix element of the Sx had a certain form. Now Sy has matrix elements h bar over 2, 0, minus I, 0. Okay, so now I have to be careful to put in the proper sign. Okay, so this is again up, down, okay, up, down. So that means, okay, just to summarize, up Sy down is this one is equal to minus I, and down Sy up is plus I. So those are the only finite terms that will survive that inner product. Okay, so just please check my algebra. So up, and down over there is going to give me minus I, and down and up is going to give me I, obviously also the h bar over 2. Okay, so I shouldn't forget the h bar over 2's. Okay, so this is going to be equal to 1/2 h bar over 2. Let's see what we have. First of all, we should get something real, right? Because Sy is a Hermitian operator, so its expectation value is supposed to be real, okay, associated with measurement. So, but let's just check. So I'm going to get e to the minus, okay, product of these things, I gamma b0 t times minus I already took out the h bar over 2. And then I have this down up term plus I e to the I gamma b0 t, okay, and that's it. So now you see that I can associate the sine function with this. So what do I need to do? It's going to be 1 over 2. Let me just do this. Let me take h bar over 2 out. And then if I have h bar 1 over 2I times I, okay, I'm just rewriting this 1/2. And then I have the bracket again. So I have I times the bracket. So you see this comes in with a plus sign, that comes in with a minus sign, so it's going to be the minus sign. Okay, so it's going to be h bar over 2, okay, times sine omega okay, Larmor times t. Okay, so what has happened? If I wait for some amount of time, I am going to go from this direction in the, okay, so this is at time equal to 0. Okay, the expectation value of the spin is going to be minus h bar over 2. But then if I wait a little bit more, so how much more? Okay, t times omega L equal to pi over 2, in which case the cosine becomes 0 and the sine becomes, okay, what did I do with my minus sign? I think I missed the minus sign here. Okay, so at the later time, at that time, if I make a measurement of the spin in the y direction, I'm going to find out that it's equal to minus h bar over 2. On the other hand, at that same time, if I make a measurement of the x component of the spin, it will average to 0, right? That's where the cosine becomes 0. So what does that mean? It means there's a 50-50 probability that the spin is plus h bar over 2 or minus h bar over 2. Okay, so let's wait a little bit more. So if when I have t times omega L equal to 3 pi over 2, okay, and then I have the cosine now gives me a minus sign, and at that time the measurement of the spin in the x direction is going to give me minus h bar over 2. So the spin is now pointing, okay, well, we shouldn't say the spin, the xy component of the spin is, okay, in the minus x direction. So wait just a little bit more. This is going to be, oops, this is pi, right? And over here, now I have omega t times omega L now equal to 3 pi over 2. Okay, in that case, again, the x component of the spin will give me 0 average, but the y component now is going to give me plus h bar over 2. And finally, I can just sort of see that if t becomes, okay, this omega L times t becomes 2 pi, this has gone around and have made one period. Okay, but if you just look at what the let's just take a look at this piece. Okay, I have it in several places, but if I now look at this piece of the equation, okay, so this is our chi t, right? It's already here. Okay, now what happens when I increase t, okay, such that omega lt is equal to 2 pi? What do these factors become? If t is equal to, okay, omega L, okay, because what I have here is omega L over 2, right? So if I now put t times omega L equal to 2 pi, what do I get for those exponential factors?
-1.
-1, right? So what's something that's interesting here is that if when I have this chi for omega L times t equal to 2 pi, okay, is equal to minus the chi at t equal to 0. So we said that, okay, let me just move this. Okay, so we said that when we go around, okay, so when we go around once, okay, so I am pointing in this direction, in that direction, in that direction, in that direction, but throughout that time, I am also developing a phase which becomes -1 when I make a full revolution. Now that -1 is not too significant because there is a -1, okay, multiplying this term and a -1 multiplying that term. That's why, for example, as x returns back to its own value. Okay, so I don't have to worry about that -1. But if I make an interference type of measurement, what does that mean? Okay, so here comes my, okay, up x, and I just divide the path of the electron into 2, and then I combine them over here. Okay, suppose I put a magnetic field on one of them. So this is my B0. So that this particle spends some time inside that magnetic field. And I adjust it such that it makes one full revolution. Okay, so there is a 2 pi revolution that we have here. So what happens? Over here I have the particle coming in with up x, whereas on this side it's coming in with minus up x. So when I add them up over here, I get destructive interference. Okay, so that development of a minus sign, because I'm now adding these two wave functions, when I add them up, I'm going to get 0. Okay, so this is something actually measurable, and it says that if you rotate the spin around it by 2 pi, you don't get the original function. Okay, that's why we cannot find these functions in ordinary orbital angular momentum calculations, because these things do not map to themselves after a rotation of 2 pi. They just go to their negative. Okay, so in order to get the same object back, you have to rotate it around by 4 pi. Okay, so there was this celebrity a few years ago who, instead of saying making a 180 degrees turn, he said 360 degrees, and everybody made fun of him, but he was perhaps thinking about electrons, right? You never know. Okay, so let's see. Any questions? Because now we are going to start studying something a little different. All right, so we have seen how we can analyze the angular momentum. We found out that these commutational relations generate a lot of properties which automatically gave us these angular momentum states, the LMs and everything. But now I'm interested in trying to find out what happens if I have more than one angular momentum. Okay, so how can that be? Well, first of all, if you are interested in studying something like the hydrogen atom, the electron has not only a spin angular momentum, but it also has orbital angular momentum, right? So I'm going to get, in the case of, for example, a particle moving in space, we know that there is this L object, and then there's also this S object. So the total angular momentum of a particle which is moving inside a central potential is going to be L plus S. So now we will be interested in what the total angular momentum does, okay? But before we get to that more general case, there's a very important special case which involves the angular momentum of two particles with spin 1/2. Okay, so this is something we'll discuss a little later meaning next semester, because we don't have time this semester. Okay, so what we'll do is we'll look at the total spin angular momentum, okay, of two okay, S 1/2 particles. Okay, so these are perhaps two electrons. Okay, and I'm interested in what the total angular momentum of two electrons are. So I have one electron here, okay, another electron there. You see, I'm not looking at the orbital angular momentum. I am not looking at how they are, okay, rotating around one another or anything like that. Okay, I'm looking at the total angular momentum. So these things have angular momenta. This one has angular momentum S1. This one has angular momentum S2. And we know how these things behave. Okay, individual particles, we know how those angular momenta behave. And I just now want to look at what is going to happen when I look at the sum. Okay, so we are going to define S without a subscript as S1 plus S2. Okay, so that's going to be our total angular momentum. So what does that mean? Well, that means that if I look at any component of this, Sx is going to be the x component of the first object plus the x component of the second object. The Sy is going to be the y component of the first electron, y component of the second electron. Sz is equal to Sz1 plus Sz2. So these are two separate particles, okay, in some sense independent at this stage. So we do not have any effect of one on the other at this stage. So things, okay, these S operators for different particles, they just commute. Okay, so this Sx1 commutes with Sx2, or Sx1 commutes with Sy2. So for these two different particles, okay, just think of them as if they are in different rooms or something. Okay, so there's a certain set of commutation relations which involve Sx1, Sy1, and Sz1, which we know. Similarly for Sx2, Sy2, Sz2, but we do not have any, okay, interference, if you like, between the two. So we say that, okay, Sx1, for example, commutes with Sx2. Okay, I'm not going to list all of them, but also Sx1 commutes with Sy2, okay, because particle 1 is independent from particle 2. Yes?
John, can you explain this? They are
No. Okay, if you have angular momenta associated with two objects, even classically, right? So if I have two classical objects, something like a disk, perhaps, okay, so this is rotating and has some angular momentum L1 in that direction, and this one has some angular momentum, right, L2 in that direction, I can always define total angular momentum is L1 plus L2, right? I don't have to have common axes for these things. Okay, in fact, it's just vector quantities. Okay, but now let's see how these things are behaving, okay, when I look at the commutation relations of this Sx, Sy, and Sc. So if I now look at the commutation of Sx and Sy, that's going to be commutator of Sx1 plus Sx2 with Sy1 plus Sy2. Okay? Now, almost everything commutes, well, not almost everything, but Sx1 and Sy1 do not commute, and Sx2 and Sy2 do not commute, right? Because those are the x and y components for the same particle. So this is going to give me Sx1 with Sy1, and then I also have Sx2 with Sy2. Okay, so this first one is I h bar Sv1, standard commutation relation that we know. This one is I h bar Sz2. So it's going to be I h bar Sz for the total spin angular momentum. But you see now what happened. Let's just write this down. Sx Sy is equal to that. And again, I can just generalize this to other components. Sy Sz is going to be I h bar Sy Sz is going to be I h bar Sx, and Sz Sx is going to be I h bar Sy. Okay, so this object, this total S, is also an angular momentum operator, okay, perhaps not too surprising, and that will have its own eigenstates. Okay, so if I now look at, okay, so all latecomers should take notice of this. We have 2 hours of class on Monday. Okay, so what does that mean? Well, that means that this object, S, which is made up of S1 plus S2, okay, also has its S squared operator. We have to be careful what S squared is. It's going to be S1 squared plus S2 squared plus S1 S2 plus S2 S1, etc. Okay? But we have that, and that is going to have its own eigenstates. So it's going to have SMS type of eigenstates, right? Because all you need to obtain these are these commutation relations. If you just have those commutation relations, if you just have those 3 commutation relations, you always get this, okay? Doesn't really matter whether it's S or L or whatever. As long as you have these commutation relations, you are going to get eigenstates here which look like S times S plus 1 h bar squared, SMS, and Sz, SMS is going to be equal to what? MS h bar SMS. Not only that, but since we are going to need them, I have these S plus or minus operators in this space, which is going to be, okay, okay, Sx, right, plus or minus I sy. So that's going to be sx1 plus sx2 plus or minus I sy1. Okay, let's put it this way, plus sy2. Okay, so remove this. Okay, so I'm going to get these raising and lowering operators. Okay, I don't have to do the algebra again because this is all I need. You see, this is the power of this technique. If I have commutation relations that go like that, it always implies that. And not only that, now I can use these things to raise and lower this stuff. So it's going to be S, how are we doing on time? Okay, almost there. Okay, so S plus S ms is going to be equal to h bar square root of s plus 1 minus ms plus 1, okay, times s ms plus 1. So that's our raising operator. And s minus s ms is going to be h bar square root of s plus 1 minus ms minus 1, right? Please check my algebra. S ms minus 1. So it has these eigenstates. We do not yet know what they are, okay? The total angular momentum of two objects, two spin 1 half objects, we look at their total angular momentum when I add their angular momenta, is going to have again the same structure. But now I don't know yet what these things are. Okay, so we have to really figure that out. Okay, so this is a good place to stop. Let's have our break and we'll continue.